Yeah, all right. Good afternoon, everyone. Welcome to the afternoon section. I'm the section chair. My name is Kunling Yang. I'm the associate professor in the Department of Chemical and Biomolecular Engineering at the National University of Singapore. This afternoon, we are very honored to have three speakers in the section. So we will start with the first speaker, Dr. Mohanad Harbawi. So he's obtained his master and doctorate degree from the University of Putra, Malaysia. And he is currently an associate professor at the Department of Chemical Engineering, King Saud University in Saudi Arabia. His area of expertise are process safety, toxicology, and environmental impact assessment. So he has published more than 50 papers. He has received several research grants from the various organizations, including Petronas, oil companies, and the Kingdom of Saudi Arabia National Science, Technology, and Innovation Plan. He is currently working on several research projects, including fire explosion and the conversion of biomass waste into valuable products, such as hydrochar and hydrogel. So today he is going to tell us about his research on the hydrothermal carbonization of biomass. Dr. Mohanad, the floor is yours. Please.
Thank you very much. Thank you very much, Professor Yang. Thank you very much all for attending and giving me opportunity to present my work here. Before I begin, I would like to thank my collaborator, Ian, Dr. Yang Yin. He's also working with us in this project as external investigator. I have been working with him since I think 2010. We were colleagues in Malaysian University Technology Mara at that time. Since then, we have worked together in different projects, and now currently he's working with me. Well, in this presentation, first I will I will give a brief introduction about hydrothermal carbonization of biomass. Then I will move to present some of the preliminary results we obtained in this project. I will start with the general introduction about hydrothermal carbonization. Hydrothermal carbonization utilizes high pressure vessel such as autoclave, the one we see here. This is one example. There are many examples, but this is maybe a simple one currently we are using. And to convert biomass, different biomass, also can convert glucose, fructose to hydrochar. Normally the temperature is between 160 to 250. This can go up also more than 250, but what we are using now is this autoclave is the maximum temperature we can use is up to 250. Well, hydrochar may contain some carbon microspheres. These carbon microspheres have many advantages in absorption of pollutant in industry. So similar to activated carbon, but activated carbons have higher surface area. It can go up to 2,000 meter per gram or meter square per gram or more. Hydrochar normally is not more than 60 or can go up to maybe 100, but seldom. Normally is below that, below 50. But to produce activated carbon, this is energy intensive and expensive, and usually can consume a lot of energy. Hydrochar can be produced at low temperature, and it can be produced in one step only. It's very cheap and doesn't have any environmental effect. So it's environmental friendly product. As you see from these two, the top two images, here we can see visible carbon microspheres from glucose and sucrose, and this is quite easy to produce. It's about maybe these two images about 180, and the residence time is about 3 hours or 4. The below two images, this is we have obtained currently from date molasses, which contain 40% glucose. Image A is at 2:30 and 3 hours residence time. Image B at 2:30 and 4 hours. So it's we can see from image B, the more we have residence time, the carbon microsphere can develop bigger. The spheres will be visible and completed. Anyway, to produce carbon microspheres from zero material is not that easy as the one for glucose and sucrose. Different authors have tried or synthesized carbon microsphere from different biomasses. Zubair and his team produced carbon microsphere at 130 and 6 hour from organic shell, and you see some spheres are developed here, but not that clear maybe. And Zhang et al. Also produced carbon microsphere at 240 in 1 hour. Costa also produced visible carbon microsphere, but the residence time is about 48 hours. Sevilla also produced carbon microsphere as here. We have different parameters which affect the production of hydrochar, such as temperature, residence time, freshwater pH, substrate concentrations, and heating rate. The temperature, will go quickly through these parameters. Temperature is very important, maybe is the most important parameter. Temperature is normally the higher temperature we can we increase, the easier or the more hydrochar or carbon microsphere we can obtain, but this is not always, because if we go above maybe 250 for some biomasses, the carbon microsphere demolish. We don't see any more carbon microsphere. It's become hydrochar without forming carbon microspheres. Hockman found that the yield of hydrochar decreases for lignocellulose, decreases from 69% to 50 when the temperature increases from 215 to 225 degrees centigrade. Hassan found also for grape seeds, the hydrochar yields decrease with temperature, as you see, from almost 69 to about 61 here, when the temperature increases from 200 to 225. The second parameter is residence time. Residence time is also important, but different studies concluded that the residence time should be more than 2 hours. We sometimes cannot obtain hydrochar or carbon microsphere at short residence time, like 30 seconds or 1 hour. Depends on the material, the biomass. Some materials can obtain easily, but some usually is difficult to obtain at short residence time. As you see from this figure, Hassan found that for grape seeds, the yield of hydrochar decreases or increases residence time. But however, the residence time, the shortest residence time he uses is 6 hours. For 6 hours, normally the hydrochar or carbon microsphere will appear visible. But also depends, because we have tried different materials or different biomass from palm date and from suburban. Not always we get at shorter than 6 hours. As we see, as we see from this figure, which will increase the residence time from 30 minutes to 24 hours. And we see at 30 minutes, we couldn't obtain, he couldn't obtain visible carbon microsphere. So they increased the time to 6 hours. So we can see there are some microspheres there, but on 24 hours, visible microsphere developed. Freshwater pH is also another parameter affecting the formation of carbon microsphere. Liang et al. Found lowering pH will enhance the carbon microsphere formation from starch in the early stage of the reaction. Young also investigated the hydrothermal carbonization of husk and nuts at the range of 4 to 13. The results shows that at pH 13, the yield of product reduced, significantly reduced, while at the pH range from 4 to 10, there is not much changes. Reza also found that the acidic freshwater results in hydrochar with a greater surface area, volume, and lower pore size. Zhang found that for cotton fibers, additional of CO4 supports the formation of carbon microsphere at lower temperature. As we see here, at 210, the formation of microsphere is not visible, but the increasing the temperature, the carbon microsphere developed, especially maybe at 330. Well, before adding the CuSO4, the results was there is no carbon microsphere even in 330. Zhang also prepared hydrochar composed carbon microsphere by using different acids, as we see, especially for HNO3, the spheres are developed clearly and visible here. Flora found that absorption capacity for hydrochar with HCl is increased. This is due to the increasing of surface area. Normally, we use only deionized water, and this will not produce high surface area. It's usually varying from 10 to about 50. But if we use some acids to activate the hydrochar, so we will get normally high surface area. We increase the surface area, and that increase the absorption capacity. The other parameter, substrate concentration, the usually high substrate concentration used will result in high productivity level, but this is not always true. Some studies like Sibila or reported that increasing the cellulose concentration will decrease the yield of hydrochar. Similar results reported by Nikovic for glucose. And the heating rate is also another parameter affecting the production of hydrochar or formation of carbon microsphere. Zhang investigated the effect of heating rate between 5 and 140 degrees C per minute for grassland, and results indicated that the yield reduced from 22 to 23% to 8 to 9% when the heating rate increased. Similar results obtained by San for corn stubble and wood chip. They found that the yield of hydrochar decreasing from 19 to 9% when the heating rate increased from 5 to 140 degrees centigrade per minute. Now I'll present some results regarding to the project which we are working currently and sponsored by the National Plan of Science, Technology and Innovation, King Abdulaziz City of Science and Technology. This project is about synthesizing carbon microsphere and hydrochar from palm biomass waste and its application in wastewater treatment. We have different palm biomass here, but majority we are the one from the waste from date palm and some from sabal palm. These are the two palm available in the country. Most of the waste come from palm date, and the country currently has about 31 million palm date tree, and each tree produces about 20 to 35 kilogram of waste, depends on the age of the palm. And there are many types of palm dates, is about 400 types, and it's not all same, different production and different fruits and different biomass. The total waste is about 800 per year, 800 metric ton. So in the Kingdom of Saudi Arabia, there is no clear or no production, commercial products from date palm waste. Only we have seen in the market for the past years charcoal, and it was quite expensive. I guess now no more. I didn't see it since a few years. And there is another application, but still I think not really well developed, is the oil for cosmetics from seeds. Some people selling it, but in small maybe quantities. So the normal way of disposing this waste is burning, traditional way of burning the waste, and this is caused so much of pollution. Other than that, they only use maybe for some traditional products, like maybe those they use for keeping, like making boxes or bags, and this is very small, consumes very small from the waste. We have many biomass from date palm, but we are focusing on the majority which leaf it and leaf stem and all the base. This contribute for the majority of the waste. Fibers also, and empty food bunch. The others also, but not much as these five types of waste, because I think per year they clean or they remove these five types about maybe 3 times from the tree. So the other type of biomass is from sabal palm. We have also sabal palm here we use for in gardens and in the street sides, but this sabal palms, the number of trees is much less than the palm, and the waste will not contribute as much as the one from palm trees. We have 3 types of waste. We have the leaf bed and leaf stem and fibers. I will present some results about sabal palm because we have 2 teams. One team is working in sabal and the other one is working in the date palm, and we recently received more results in this sabal palm. So I will present some results here about this type of palm. We used the jaw crusher to crush the biomass. If we crush the biomass, we wash the biomass and clean the dust and other materials, and then dried for at 80 degrees for about 2 days. Then we crushed it using this jaw crusher, and then we soften the material because the material is still not very soft. Then we use the laboratory plate mill, and then we use sieves to get the desired size. We have tried different size, but we found that 0.25 millimeter is giving us is acceptable results. And if we softening the material more, we didn't obtain better PET area. So we worked with these guys. And as you see here, this is what we get from this job crusher, and this is from the laboratory plate. Then we start producing the hydrochar by mixing first the biomass. We took 2.5 grams of biomass mixed with nice water for about 5 hours. Then we place it in the Teflon tubes here in the autoclave, and we seal it very well. Keep inside the oven at 230 for we selected different times, 4 to 8 hours. Some materials we obtain good microsphere at 4 hours, but some no. So we use different hours, residence time. The product we get, we separate the solid particles and using centrifuge. And then we dry it in the oven, and then for about 1 day, about 80 degrees, then we obtain the product. The product, in our case, we found that carbon microsphere present appeared in the 3 samples we have. But for palm date, we found that some biomass doesn't contain carbon microspheres, and that's why we are trying to change some parameters to obtain the carbon microsphere. The yield, we have 3 samples. Each sample for 4 hours duration and 8 hours each one. We obtained, I think the highest yield was for the leaflet is about 43%. And this figure shows the yield for the 6 samples we have. We have each sample we did 2 different times, 4 and 8 hours. And this picture shows the images. This image shows the carbon microsphere particles there, the spheres there. As you see from figure A dash, there are some carbon microspheres, but not well developed. You see maybe this part still need more time to develop, and when we increase the time from 4 to 8 hours, we obtain a better or full spheres. And this is for the first sample for fibers, and this one for B samples for EFSM. And here we can see at 8 hours, this is 4 hours, and this is 8 hours. The spheres may be demolished or because the more residence time. So 4 hours is enough for this sample, but for the previous one, 4 hours wasn't enough. And for leaflet, we found that 4 hours is also good enough to develop full spheres. Well, elementary analysis section device results shows that the carbon content in the leaflet is 8 hours is the highest here, and the ratio of oxygen to carbon and hydrogen to carbon ratios decrease with the increase of the duration, as you see these 2 columns. And this same observation reported by Ahmed Khan, who synthesized carbon microsphere from rubber wood. And This picture or this table shows the PET area. The highest we obtain for fiber 8 hours is about almost 60, but the other samples is maybe less than that. But according to the literature, if the surface area below 60, this means the microsphere, the carbon microsphere, not fully developed porous material. So we concluded that what we have developed will not give a good result as activated carbon because the surface area is quite low. So the same observation by other people reported for different biomass is about 10 to 35 meters square per gram, and we obtain also maybe slightly higher than we used what we have obtained for adsorption with ethylene blue to test the efficiency of removing the pollutant from wastewater. So we obtained the highest we obtained for leaflet is about 40 milligram per gram, and this is quite low comparing to activated carbon. But however, the full results is illustrated in this figure, but this gives some indication that the material can be used as a raw because we haven't activated using any chemicals, or we haven't do any chemical or physical activation yet. So the absorption data appear to fit the more model better than Friedrich model. So, and this is reported also by Zhang, who also tested his hydrochar for methyl blue absorption. And then this suggested that the mechanism we obtain is absorption, and the absorption will appear only on the surface. So there is no porous material, or the molecules of the methylene blue is bigger than the holes of the pore inside the surface. So that's why we are trying to improve the surface area and the porosity of the material. Anyway, we also confirm our result with the Gianco research. Also, they obtained hydrochar with surface area, low surface area below 60, and they assumed the removal of methylene blue happened due to the electrostatic interaction. Some functional groups here in our project, we found that the acetic, the oxygenated functional group is about 0.4 to 0.5 millimole per gram, and this is not that much. So we need to increase this one. Before I go for future work, I conclude what we have obtained here. We developed, or we obtained carbon microsphere, successfully obtained it using biomass from sapal palm, and we tested for removal of methylene blue, and it's what anyway the result is still low, and this is good indication that the material could be used for removal of pollutant from wastewater. So we are our target, or our main objectives is to improve the surface area by chemical activation, for example, using KOH or HCl, and we will also use the ionic liquid to increase the surface area, and also DS, and these two chemicals are novel. We synthesize in our lab, and we expect a better result than maybe KOH and HCl and other chemicals, because ionic liquids and DS are less toxic, and some of them are green. Toxicity is level is very low, and we expect a better result from environmental side. I acknowledge the fund provided by the National Plan for Science and Technology. And finally, we have recently received one acceptance for a paper in biomass conversion and biorefinery. The impact factor is 4.9. Some references we used in our work here, and then I end my presentation. And thank you very much for your listening. And if you have any question, please go ahead and ask. Thank you.
Thank you, Mohanad, for the talk. Do we have any questions from the audience for Dr. Mohanad? Maybe let me start it with questions. So you mentioned that you use a methylene blue as a model dye for absorption experiment, right? And we know that the methylene blue is carry a positive charge. So does that mean that you won't be able to use a hydrochar for those positively charged dyes, such as a tryptophan blue? Negatively charged, sorry, the negatively charged, because the hydrochar is negatively charged, right? So that's why you can absorb positively charged your methylene blue. How about those dye which is negatively charged, such as tryptophan blue?
Well, actually, the problem is the hydrochar we produce now will absorb. We realize that we will absorb some pollutant with a small molecule. Means methylene blue or others will only the absorption will be only on the surface. So what we are trying to do, we are trying like to increase the tunnel, the one on the surface to absorb these pollutants. It depends on the molecular structure. Some have a big molecular structure will not go inside the spheres. That's why we receive a small surface area when you tested using BET. The nitrogen they use will go inside the tunnel inside these spheres, so that will increase the surface area. But we are trying also to increase, as I said, using different methods. We expect to have a better result, but currently we don't expect to have a good results for other pollutants, because methylene blue, I think, one of the easiest dye used for removal. Most of people prefer to test the materials using methylene blue because it's quite simple.
Yeah. Okay, thank you.
Thank you very much.
Thank you. Any other questions from the audience? You can either unmute yourself or just type into the Q&A section, use a chat function. Yeah. Let me ask you another question. So when you produce this hydrochar, do you need to fill the environment, the atmosphere, with a nitrogen or other inner gas?
Do you mean to test it?
No, to protect it, because if you increase the temperature under the atmosphere, right, with the oxygen, the carbon may be oxidized, right? Is that a problem, or you need to protect the hydrochar with nitrogen or other inner gas?
Oh, all right. Actually, that's with CO2. That's maybe physical activation. It's some
CO2. Yeah, CO2. I see.
Yeah.
Okay, let's chance to ask Dr. Mohanad the question. Anyone? Okay, if no, let's thank Dr. Mohanad for his talk, and we'll move on to the next speaker. Thank you.